Good afternoon, everyone. Thank you for joining us today for the Calculating Energy Costs webinar. My name is Beth, and I will be your host today. We'd like to start this afternoon off with a safety moment. Safety is a core value of PGE, and we want to remind you to be safe around electricity. As you consider installing or retrofitting new equipment, please keep safety in mind. We also want to encourage your family and staff to be prepared with an outage kit, and you can visit our website for more safety information. We also want to thank the Energy Trust of Oregon and the Northwest Energy Efficiency Alliance for their support in co-sponsoring this series of free energy efficiency trainings that are open to all Northwest utilities and their customers. Before I introduce this afternoon's presenter, I'd like to show you some tools you'll be using during the webinar. To the right of your screen, you'll see several windows: the participants window, the chat window, and at the end of the webinar, you'll see the polling window. If you have any questions during the webinar, you can submit them to me, the host, through chat, and I will ask the presenter these questions at the end of the webinar. Because this will be an informal session, if you'd like to share an example or you have a question you'd like the instructor to address immediately, please feel free to use the Raise Your Hand icon, which is provided at the bottom of the participants window. And if you could take a moment to practice using that at this time, the Raise Hand icon looks like a hand. John McLean is using it right now. You can press it to raise your hand. There we go. Scott's using it. And click on it again, and you will lower your hand. So if you raise your hand during the session, I'll interrupt and ask John your question and unmute you to do so. Thank you very much. Underneath the Quick Start tab at the top left-hand corner of your screen, you'll see several tools, which I'm circling here. The arrow, the pointer arrow, the text tool, and a marker tool. The presenter will be asking you to use these during specific slides during the session. And now I'd like to introduce today's presenter, John McLean. John is the Training and Education Project Manager for Portland General Electric for our business customer trainings. He has over 42 years of wide-ranging utility experience, including substation field distributions, including distribution field operations, information systems, corporate planning, budget management, and energy efficiency program management. He holds a BS in Business Administration and an MBA in Organizational Effectiveness. John is adjunct faculty at Clackamas Community College and also at Marylhurst University, where he teaches several courses as part of the MBA in Sustainability program. And now at this time, I'd like to hand the presentation over to John. John?
Thank you, Beth. Welcome, everyone. We're having great weather here in the Willamette Valley of Oregon. I hope wherever you're at, you're having equally good weather. Today's webinar, we assume that you are a non-technical manager, staff, or other interested professional that has a lot of energy-intensive systems. We'll be dealing with non-residential examples, work, office, campus, governmental, industrial process, but the concepts we discussed today will also be useful in a residential application as well. We assume that you want to learn the fundamentals. You can only do so much in an hour, but we will cover basic concepts in electricity and management, but those concepts also have use in natural gas, water, carbon footprint, other resources as well. In the short time, we can't cover everything, but we will cover the ones most commonly that I hear from our customers at our local utility and around the Northwest. And it all begins with the ability to calculate energy costs. My first slide is kind of a reminder of why we start a fundamentals class with measuring, and that is, as Peter Drucker would say, what gets measured gets managed. We all have gotten energy bills at home or sometimes at business and wondered why the costs were so different than the prior month or the prior year. Gee, what could I do to kind of reduce our footprint in electricity, gas, water, and other resources? So it does start with measuring. In looking on reading labels. by federal code, every piece of equipment has to have labels that tell you information about electricity, whether the watts, volts, amps, efficiency. And so reading labels is probably the first thing that I find business people don't do when they buy or use equipment. So let's get started with the next slide. You may also be familiar with ISO standards in international standards organizations, the Deming cycle, process improvement, Lean, Six Sigma. There's always a cycle. Plan, do, check, act is the cycle here that I've pointed out in the center of this slide. And the two phases that we'll talk about today that measuring has the most impact on is the plan. The planning stage talks about current state. When you do start measuring, you'll develop your own baseline. You'll discover what are the kind of key indicators. Is it kilowatt hours per square foot? Those kinds of things. You'll set some goals. You'll identify a team of people, and they'll come up with an action plan, of which will put you into the do cycle. The next cycle where today's webinar will help you with is once something has changed, you'll begin monitoring, measuring, reporting. Maybe even you hear the word energy audit or an audit, post-audit, and take some corrective actions, or congratulations, it worked exactly like you thought it would. So in the plan, do, check, act cycle, the planning cycle and the checking cycle is where measuring and monitoring is the most critical. So let's get started with the basics of electricity. What is electricity? How do we measure it? We'll use, as in most texts that I read, the garden hose is the equivalent that most of us can understand about features of electricity. Let's look at, assume that you're taking a shower in the morning and suddenly the shower starts getting lower and lower and lower pressure because the whole neighborhood has simply fired up all of their sprinkler systems in their front yards. You would know right away, I have a low water pressure issue. If the same thing happens in the electric business and you want to do something and everybody in a certain area fires up their motors and all their equipment at once, you could have a low voltage problem. So volt is the first dimension of electricity. It's the amount of force or potential applied. The equivalent in the water system would be pounds per square inch. The pressure in the system has to be high enough to run all the equipment and things hooked up to that system. The second thing we know from our water hose examples is if I want to move a whole lot of water from one place to another to run a piece of equipment, in my case, my example is a little Rainbird sprinkler, required a lot of water to make that work, and a little half-inch hose was not big enough. I had to get a bigger hose to move more water to that device. So the size of the hose also affects the amount of water I can get from A to B. In the electric side, you would find that that is going to be the mighty amp. So when you hear people discussing or staff discussing, we have an amps issue, we're talking about the volume of power that has to get from A to B. And it's all about the wire size, and we'll talk about that a little later, that the bigger the hose, the more water, then the bigger the wire, the more amps that can be moved from A to B. When we take those two and multiply one times the other, that's when we'll get the watt. So volts times the amps gives you wattage. This is the single phase formula. All of residential and most commercial will have the single phase service. I'm going to introduce a few more concepts you may hear. We're not going to talk about today, but you should at least be familiar with them. And that is watts equals volts times amps times the square root of 3. That's a constant 1.7 something times the power factor, which is normally a number between 0 and 1. And for 99.5% of our customers, the power factor is considered to be 1. So if you have a three-phase operation, you may have a formula slightly more complicated. Also on some bills, again, a very small portion, you may have a power factor issue. You may see kVARs, KVAR. You may see reactive loads. Again, this would be a more advanced class on power for very large industrial customers. And finally, you might hear the term the ohm. The ohm is, it deals with the resistance to the flow of energy, and it's not on your bill. I've never heard of a customer calling a specialist and going, I've got an ohms problem. It's usually in the control systems and electronics rather than electrical power industry. But if you hear ohms and Ohm's law, all of this is related to electricity in a more complex way. So we're going to talk about volts, amps, and watts, all things that you should find on the labels to your products and systems within your businesses. So the next thing we look at is if the bill is what we're trying to manage and it's the electricity bill, most of your bill, 90% of it, plus or minus a little bit, is going to be kilowatt hours times a price for that particular line item. Most of us think of an acronym like KWH meaning one thing. If I tell you Portland Trail Blazers basketball, they're a member of the NBA, that's National Basketball Association. So there's only 3 letters, but it stands for one thing, one organization. In this case, KWH really is 3 separate concepts laminated together. So let's break those apart. The first one takes us back to the good old metric system. K means 1,000. In the papers, you might read about power plants or wind turbines that are measured in MWs, megawatts. This means 6 zeros, 10 to the 6. You could see gigawatts. My personal favorite, if you do a search engine on the internet and find all these, is the yottawatt. The big letter Y stands for 10 to the 24th, 24 zeros. So if you've got a yottawatt, you are setting world records. Most of us deal in K and M watts. The middle part of the acronym on your bill, it's all about the W, but it could be a V. You could have KV. If you look outside and you see those wood poles with the power on the top, it's likely that it's probably 12,000 volts phase to phase. That's 12 kV would be the terminology. So don't get thrown by the fact that the middle part of the acronym could be a W, a V, an A, an O, or some other letter of measure of power. So most of the time we talk about kW, but the equipment you buy is labeled with a W, and you have to make the conversion. The final part of the acronym is about the hours, the time dimension. Basically, when you buy your equipment, you purchase it and the label says this equipment will use a certain amount of watts or kW. What controls your bill is how many hours of operation is that equipment on. This is probably the most under-measured part of managing energy is people know what the watt is. They can easily convert it to kW. But making an estimate of how long really does the equipment operate is the least monitored piece of managing energy. It's as simple as walking out of the room, turn the lights off, but if I ask you how many hours of operation does a particular piece of equipment actually on for a month or a year, I get blank stares and, oh, we'll have to go out and study that. You may see instead of KWH, KWA, or even MWA. The A stands for annual. In other words, 8,760 hours a year would be something like an exit sign. It's on 24 hours a day, and it's on 365 days a year. 365 times 24 gets you 8,760. If you're budgeting or monitoring, you would know, oh, I have a whole lot of exit signs at a certain amount of wattage times 8,760 hours if I'm doing an annual budget cycle. If you have staff that says something is on for 50% of the time, then you know it's half of 8,760. So you can see that 8,760 is a pretty useful number that most budget managers that work with energy bills have at their fingertips. So 3-part acronym. The first part is how many zeros. The middle part is which dimension am I looking at. K-watts is the most common, but it could be KV. And the dimension of H is managing the time. So this is a useful chart to remind ourselves of how this acronym really works. So let's get started with some of the simplest math. How much energy does a particular piece of equipment use? Here's the simple formula. Watts divided by 1,000 times hours. gets you kilowatt hours. In this example, we have 20 light bulbs at 100 watts each. That gives me 20 times 100 is 2,000 watts. I divide by 1,000. So for every hour of use, we have 2 kWh per hour. I had one manager, very bright person, said, I want to get my whole staff involved in this monitoring of energy and put a label by every switch on equipment to let them know for every hour it's on, here's how much kilowatt hours this thing uses. And that got the staff kind of focused in on, oh, this thing actually has an impact on the bill, and by me paying attention to how many hours it's on, I'm having an effect. So let's do a little math. This is where I would ask you to go to the upper left-hand corner or upper left part of your screen, and they have tools up there. You can use the arrow, you can grab a pencil, you can grab a check mark, and you're going to see if you can't help me answer this question. How many kilowatt hours are used by a 60-watt light bulb? It's on 10 hours a day for the next 30 days. This is a pretty common question that people feel sometimes they forget the formula. So here's the hint at the bottom. So take your best guess. Use that cursor. Here's my arrow. You can see I can move it around by clicking. And select for me what you think this answer is. Is it 1 kWh, 5 kWh, 18, or 180? Thank you, Scott. Scott's on it. Tom's on it. This is good participation. Now, this may seem trivial while the rest of you are finding your interactive tool and helping me answer this. I met with a business person who was a car sales operation, and on their used car lot, they had 1,000 bulbs in strings so that it would shine on all the cars at night on the main drag. And so this little example might be a few kilowatt hours, but when you multiply times 1,000 bulbs, he suddenly realized that he was spending over $800 a month on lighting, and that was something he should probably come up with a project and get changed. Well, it looks like I have a very bright group today. They all said 18 kilowatt hours, so they're either all together right or all together not, and the answer is 18 kilowatt hours. 60 divided by 1,000 times 10 times 30 gets you 18. So let's look at the next part of this question. What if I switch this to compact fluorescence? So now I have a compact fluorescent, and now I'm going to change it to, instead of 60 watts, an 18-watt light bulb. It's still on for the same number of hours, and see if you can help me what is the kilowatt hours of the new load would be for 30 days. And again, use your, pick your symbol that you'd like. I'm going to pick the check mark, so you can put a check mark. Which one of these do you think now is going to be the answer? Scott's on top of things. You all think it's going to be 5 kWh, and sure enough, the math comes in at 18 divided by 1,000 times the hours, 5.4 kilowatt hours. So this shows you how simple it can be, and that everyone on a staff ought to be able to have some idea of making these calculations. So let's look at an example of fun one that I like to include. You find these formulas can be used everywhere, not just at work or at home, but even in the movies. So I'm thinking about the game Jeopardy. Here's the answer is 1,210,000,000 watts. And I'm trying to think of a particular movie where this was used as a main theme. And so I'm going to give you a couple of hints. The first hint is this particular vehicle. This happens to be an electric vehicle. And sure enough, it has this special device in it called the flux capacitor. And for those of you that have ever seen the series Back to the Future, you know that this was Doc Brown's problem of when you go back in time, where in the heck was he going to get 1.21 gigawatts? And here's an example of that. It's not KW, it's not MW. He was looking for GWs. And it turns out that the only place that you could find that kind of power was, in fact, lightning, if you knew where lightning struck, for those of you who've seen the movie. So even in the movies, I could ask the question of Doc Brown, well, great, you found your power, but if I'm the energy manager, how many kilowatt hours and what does it cost to run this vehicle each trip? And the math would look like this. How many kilowatt hours does it take to charge this electric vehicle in 1 second? And the answer would be, you have the formula. Here's 1,210,000,000 watts. We know that from reading the label on this car. It's going to have to be by federal law labeled 1.2 billion. Divide by 1,000 times the hours. In this case, 1 second is 1/3600th of an hour. It takes 336 kilowatt hours per trip. If you paid 10 cents a kilowatt hour, to keep the math simple, it would cost you $33.60 per trip. You can see why I would say electric vehicles are a very cost-effective mode of transportation, even if it is a time machine. So let's look at some other examples that you may be in meetings if you're in the business community, you might hear tons of air conditioning, or you might hear horsepower. So let's deal with tons of air conditioning first. Tons can be converted to watts. But here's the second most important concept to realize when you're buying equipment or operating equipment. They all have, when it's air conditioners and motors, efficiency ratings. In this case, Energy Efficiency Rating, EER, or SEER, Seasonal Energy Efficiency Rating. And there's some other acronym ratings for efficiency. Talk to staff, vendors, or talk to your local utility. I'll show you some numbers of some people who can help you with any particular piece of equipment. In this case, you can go out and buy a 5-ton unit at 10 EER, or you can buy a 5-ton unit at 14 EER. The difference is when you run this formula, 6,000 watts is the rating of the first one, and 4286 on the second. What that means is there's a 40% higher energy bill for the next 10 to 15 years for buying this air conditioner that is 6,000 watts than if you had bought the air conditioner. It might be a little more expensive, but it's higher efficiency. This is a common problem I find with businesses that have a split between the capital budget and the O&M budget. If you're a school district, a governmental agency, or even a large corporation, the capital budget and the operating budget are two different things. And the energy bills are paid out of O&M, while the purchasing is paid out of capital. So your purchasing manager might say, wow, look at the great deal I got on this 5-ton unit. And the operating manager is going, doggone it, you should have bought the one that has the 14 EER because you just locked in higher budgets for me. Or if you're replacing it, he could have been congratulated of, you just reduced my budget by 40%. So get the purchasing manager involved and get some of these numbers and formulas reviewed by not only the operating side, but the purchasing side of the business. Motors have the same exact issue. Pay attention to the efficiency rating. In this example, the label will tell you what the efficiency rating is of the motor. If you apply that to this formula, you will get different wattage uses for two different pieces of equipment. In this case, 5% more energy used by the motor at 88% compared to the one at 92%. If you're a large commercial or industrial customer and you've got lots of motors, fans, drills, anything running by motors, air compressors, the efficiency rating of that equipment is crucial if you have a whole lot of hours of use each year. 5% reduction in the energy can be pretty substantial. So tons and horsepower can be converted to watts with these formulas. I had one customer see this, and if you have operations to where if something breaks in the middle of the night or breaks on the weekend, you don't want to wait until Monday to replace it. It's an emergency purchase. He put his specifications labels on the equipment, so even though he wasn't around, when the equipment got replaced, it said make sure whatever you replace this with has a certain energy efficiency specification to go with it, so that they never got locked in through an emergency purchase after hours. I thought that was a very good suggestion. So let's talk about amps a little bit. Here's two 60 horsepower motors. A customer is going to put in this piece of equipment. This is a pretty good sized motor, and has a choice between two motors. They are both the same efficiency, therefore the same wattage. But one says 480 volts and the other one says 240 volts. So even though these will have exactly the same impact on the bill, they're both 48,000 watts times the number of hours of use, they can have different effects of installation costs. If this motor appears on the other side of the building from your panel where the service is, you may have a lot of feet of cable to serve this motor. If it's 100 amps versus 200 amps, 480 volt times 100 is 48,000. 240 times 200 is 48,000. This will be twice the wire size, at least. Well, bigger amps leads to bigger wire from our first discussion about the garden hoses. Bigger installation costs, if that's copper, that's going to be more expensive, and line loss over that line is a function of how many amps, not the volts. I had one example of someone wanting to add a piece of equipment, and the 200 amps pushed them beyond the capacity of the panel, and they were going to have to replace the whole panel in order to put in this piece of equipment. This would be the equivalent of in your home, you have a 200 amp capacity panel in your garage. That's code for any new home, 200 amps, but if you wanted to exceed that, you'd have to replace that whole panel if you wanted to put in special extra equipment that pushed you over that. So buying the 480 volt motor might save you a lot on installation costs. So watch out for the amps. It can be a very important measurement and decision-making part of construction projects. So here's a little cheat sheet that I have found customers telling me it's useful. They can print it off. They can put it on the bulletin board. Some people want the procedural way, give me step 1, 2, 3, 4. Others go, I'm good at algebra, just give me the formula. So here's the 1, 2, 3, 4 is find the W. Find it on the label. If the label is not readable, you may actually have to get some expertise to help you measure the volts and the amps and come up with what the wattage is, especially for older equipment. Then divide by 1,000 to get to kW, then how many hours of use to get to kWh, and then times the price. So these are the 4 steps. Find the W, then the K, then the H, times the price. That tells you what this piece of equipment is going to cost on an hourly, monthly, or annual basis. If you like the algebra, it's watts divided by 1,000 times the hours times the price. So that's a little cheat sheet of the core of today's tools. So let's do another fun participation. Again, you can use whichever tool you'd like. What are the power costs for lighting an office area? 40 fixtures. Each fixture has 2 lamps, but it's 90 watt per fixture. So sometimes people will talk about the fixtures and the wattage, and some people will talk about the lamps. Lights are on 10 hours a day, 7 days a week in this particular application. We'll assume an 8 cents per kilowatt hour, which is less than the national average for electricity for commercial, and we'll assume that they're looking at it 30 days per month. So let's take those calculators or smartphones and help me out on what you think the right answer would be for a monthly bill for 40 fixtures in this little office space. You can imagine if you were applying this to an office building. The one we work in downtown here is the World Trade Center. It's got 17 floors. If they did this calculation, there would be a heck of a lot more than 40 fixtures. It might be 400, or in some cases of a complex might be even 4,000. So this example will just get you started. Tom and some others think it's $86.40, and sure enough, they are right on. 40 fixtures at 90 watts, divide by 1,000 times 300 hours times 8 cents. Now, the most common mistake I have found with doing these calculations is getting the zero in the right place. Quite often, people will think it's either cheaper or more expensive, So I've never been able to do this in my head. I always write it down, make sure I've got the zeros in the right place. So that was well done. So I'm going to lead you through example 2 here. A customer has a choice between 2 air conditioning units. One uses 12,000 watts and one uses, 1,200 watts, and one uses 1,000 watts. Obviously, the 1,000 watt machine is a little more efficient, but it costs you more. So if you're going to get money for this little project and want to spend more money on the number 2 unit here because it lowers your monthly bills, you're going to have to convince a budget manager somewhere to spend $100 more. And the most common way to do that, the simplest form, is the payback period. There's a webinar coming up on the CFO perspectives, and in that course we can talk about present value and IRRs in more advanced ways. But the first rule of thumb almost every business I know of uses is the payback period. So let's assume that this air conditioner is on 6 hours a day for 4 months a year, 30 days a month. The cost in your area, we'll use 10 cents just to keep the math simple. And it's beginning, you're going to get the idea here that most energy management projects are like a word problem. You have to go out and it won't be handed to you the way I am. You'll have to do some research, a little bit like a crime scene investigator. How many years will it take to get your $100 back? So let's look at what the typical kind of approach is. First, find the W. We'll practice our own approach here. 1,200 watts versus 1,000 watts. You're saving 200 watts. So 200 watts is what we want for the W. I'm trying to figure out the savings. How much am I going to save? The next thing we'll do is divide by 1,000, 0.2 kW. Again, sometimes when you talk to facilities or vendors, they'll talk in kW. Others will just talk in Ws. But if we're going to calculate the bill savings, you have to get to kW. Then we'll look at the H. We have 4 months, 30 days in a month, 6 hours a day, 720 hours is the H. Now we have enough to do 0.2 kW times 720 times the 10 cents the price. We save $14.40 a year in this small example. If we apply that to the $100, it takes 6.9 years to get your money back. So we would say that the payback period is 6.9 years. Now, most businesses I know are somewhere between a 3 and a 5 year payback is what they call their hurdle. If you can't, I know in our company, if you can't get a payback less than 5 years, you might not even bother filling out the paperwork to request it. 3 to 5 years. Some businesses like restaurants may even be shorter, 2 years, maybe even less. So each business or industry will kind of have their own rules of thumb based on their needs. So how do I get this project approved? The answer is keep this on the list as possible but not probable. The reason is somewhere along the line somebody may pop up and say, you know what, we believe in efficiency, and it may be the Energy Trust of Oregon, it could be a federal tax credit. Here's a $50 rebate or credit of some kind of an incentive. Could even be a manufacturer's incentive. Now suddenly the payback period changed. Instead of 7 years, you have the $100 minus the 50 divided by the 1440, and you end up with 3.5 years. So $50 rebate cut the payback period into that sweet zone of 3 to 3.5 or 3 to 5 years. If someone gave you a $60 rebate, it would drop you down below that 3 years, and the project is even better. So keep a list of these kinds of projects and keep an eye out for what are the incentives. They tend to come and go. The prices of the product may be dropped to where it's only $90 in higher cost to get the efficiency. Things change. So keep a list of all these projects. Don't simply do the analysis and then discard it once the answer is no. One of the things I like to say that the CFOs taught me is no doesn't mean never. It just means not now. So let's look at a third example to add kind of the third dimension to this getting started with measuring and monitoring energy costs. This is an example I ran across in a actual retail operation. 2 bulbs, the same exact wattage. These are both compact fluorescents, so you'd think they were equal. One's $4 and one's $5, and the immediate response would be, oh, I'll buy the cheaper bulb. So given the examples here that I've shown you, that suddenly you read the label, and one is 8,000 hours of life, and the other one lasts on average 12,000 hours, which bulb would you purchase? So I'll ask you to be realistic. If in your particular business or home situation, or if you're a landlord, use your arrow again in the upper left-hand corner, and give me a quick reaction to which bulb do you think might be the purchasing manager's decision to fill the order for 25-watt bulbs. You got to buy 100 of them. Which one do you think is going to happen in your organization? I see a check mark. Well, it looks like everybody is very enlightened and wants to go for the $5 bulb. I can tell you as a matter of fact that many purchasing managers will simply go, look, I've got to manage a capital budget, and the $4 bulb is what I'm going to get. Long-term thinking would do the analysis based on the hours of life, and you suddenly realize, I think this is a better decision if I look at this longer life bulb. So let's look at some of the math of how I would justify getting the purchasing manager, the purchasing decision to think long-term. So we have 8,000 hours life for the $4 bulb. We had mentioned it was on 10 hours a day, every day. That's 3,650 hours a year. If the bulb lasts 8,000 hours, that means that on average, these 100 bulbs are going to wear out in 2.2 years and need replacement. If I spend a buck extra, suddenly now I have the 10 hours divided, the 3,650 hours annually into the 12,000, and these bulbs won't wear out until 3.3 years. You get more than 1 year extra of lighting before you have to purchase bulbs again. In other words, over the next 6.6 years, you can spend $400 3 times on bulb A, or spend $500 2 times. And obviously, if you do the math there, 3 times at 400 is 1,200. Twice at 500 is 1,000. You save $200 in future purchasing costs by going with the bulb with the much longer life. So do the math on your purchasing of equipment. The same thing would apply to air conditioners or any other equipment. Take a look at the warranties. Take a look at the expected lives of this equipment. And it may really pan out to spend a little more money for something that has a longer life and a higher efficiency. One example I got from a customer was he reminded me that at least in this state, you have to, by law, recycle fluorescent technology. And usually that means take it to somewhere and they charge you for that recycling for commercial. This example shows how you can postpone that recycling cost out 1 year further in the distance. That's a very good benefit that can be quantified and included in this payback period if you were going to do that kind of analysis. So watch out for life. It's another important dimension. As we get to the end here, I wanted to move beyond just the math, which usually ends up in some kind of math calculation or maybe even a spreadsheet where you're monitoring the monthly bills and you have rows and columns. I know in the past I have gone into managers and go, look what's happening. And they look at this spreadsheet and go, I don't get it yet, show me. And when graphing became available, wow, when I can graph that data, you can really communicate to non-technical terms and non-technical venues what's going on, and you can ask very intelligent questions. In this example, this is 4 years worth of information. So this spreadsheet has 12 columns across the top, month by month, and 4 rows of annual bills on kilowatt hours. And I chose to, instead of January through December, I chose to put the winter, which in the Northwest, we peak in the winter most often for residential and much of the commercial. It's all about the heating load. And so I put December and January and February winter bills in the middle, which made a lot more sense. So adjust your scale to meet your operating or seasonal requirements. In this case, what I've got here is, let's see, I'll use a little different tool here. I've got 2 winters here that are high bills and 2 winters that are lower bills. And the difference between these two lines, pair of lines, was that a major equipment change happened, and the efficiency of the new equipment, they went ahead and purchased some of the most efficient equipment you can get, and it lowered the winter bills by 40% for the heating load. That's a pretty significant change just by looking at efficiency, and the payback periods were relatively quick. And this is a piece of equipment that is 15 years to 20 years life. So that made a big difference in the long run. Now let's look at a chart that some complexes, whether it's campuses or office buildings, or if your utility has meters that are digital that can measure hourly meter readings instead of monthly, let's look at a graph that at first, when I looked at this, I went, oh my God, what is that? But it didn't take too long to figure out that it was a 30-day billing period. So on this chart are 30 days worth of information. This would be a pretty big spreadsheet. And at the bottom, what you have is a 24-hour clock, and we put noon in the middle. And on the left side, you can see we've got how much load in that hour is being happening. This happens to be a school complex. And sure enough, by 8 o'clock in the morning, everybody's in school, everything's turned on. And then by 3 o'clock or so, things start winding down. So what was interesting about this is you can ask some pretty intelligent questions by looking at this chart. So I like this from a non-technical. Oh, I forgot one thing. Up here, all these are Mondays through Fridays. So that makes perfect sense. Down here is for Sundays or so, and down here is for Saturdays. So immediately it breaks into, you can see the pattern of use being different Monday through Friday than the weekends. So let's look at the questions that I was told this customer was asking. I like this one right here. The question was, I can ask a very smart question. What comes on at 1 a.m., bump in the night, and stays on for the whole night? And the answer was, the IT department finally came up and said, we think it's us. We run computer backups every night at 1 a.m. We bought some software. It automatically turns on all the computers and runs backups and diagnostics and those kinds of things. When asked how long does that take, they said about 45 minutes. And so the manager said, well, why then is my bill start low, go high, and then stays on the whole night? And the answer was, well, the software, we got a special deal on it. It can turn the equipment on. It doesn't know how to turn the equipment off. So that all throughout that evening, the computers stay on even though they aren't needed. So the deal was struck that the IT manager got some new software, and so suddenly it went on and turned off. And so all this load in here, they get to save that. And they could graphically see the change from 1 month to the next of the energy being saved. The load went bump in the night, and the shape changed. So it really helps to communicate in a non-technical way by looking at the shape. The next question was, gee, why does it take so long for this to fall off? This is the school. There aren't that many people there. It turned out in this example it was a janitorial service, and the way they kept track of what rooms they had cleaned and what rooms they hadn't cleaned was they immediately turned on all the lights in all the classrooms in the facility, and as they finished cleaning, they would turn the lights off. That way they knew what had been done and what hadn't been done. Of course, what that means is the lighting stays on until the last room is clean. You have lighting load. So they renegotiated with the janitorial service and said, I want you to turn all the lights off and only turn the lights on in the rooms you're cleaning. And so suddenly all this stuff started going away. And again, the shape looked a lot more sensible given that, gee, how many people were actually in the building. The load didn't represent that. So they saved all of that. The next thing I heard was, gee, Sundays seems to be higher than my Saturdays. What the heck is going on here? And it turns out that somebody was trying to help the budget, and they said, let's rent out the facility to its church group on the Sundays. And so they were in there, and they would fire up all the things in the certain areas, and you'd have this bump that Sundays look like this, and Saturdays you don't see that bump. Well, now you have a way to know exactly if you're charging for that service, what does it cost for us in power costs to serve that load? And you can make darn sure that what you're charging more than covers your electric bill costs. So you don't have an electric bill cost lower than what the people are actually paying for that. So again, you wouldn't change the shape, but now you have a way of calculating the difference on your average Sundays and Saturdays and making sure that your costs are covered by appropriate revenues where you can get those. So those are three really good examples where the shape of things can be extremely useful to energy management. So it isn't just monitoring and measuring and looking at numbers, it's graphing that and having ways to express that to a whole lot of people and to accomplish good decision making. So we're getting to the end. I would tell you if you're going to come up with initiatives, changing behavior, this is the idea of conservation, don't waste it. Maintenance of equipment, if you don't maintain equipment, the efficiency goes away. So changing behavior is the lowest cost thing you can do, but sometimes the hardest thing to get done is change the culture. Change the process. We talked about the janitorial service. We talked about the computer backups. You can change process, relatively inexpensive, and save energy. And finally, when the equipment fails, changing the equipment, don't lock in higher costs in the future by getting inefficient equipment. Check the label. Read the label on the life. Read the label on the efficiency. Get the best equipment you can. In the long run, that will definitely pay off. So I like splitting initiatives into behavior, process, and equipment. You'll usually find that those also are three different groups within your organization that you need to have on your team. So that's another reason why splitting it into three separate initiatives. So I guess my recommendation for next steps, start measuring. Do the simple stuff of what does my monthly bill look like, compare it with last year, develop that baseline. So establish some kind of system. Do comparisons. You can also get comparisons that for a restaurant or a hotel or an office building or a school, what is the average kilowatt hours per square foot? Again, call for help at the Energy Trust or at your local utility or a vendor even. Those standards are available and can provide useful benchmarking. Develop a list of projects, and just because they may not pan out doesn't mean you shouldn't save those and keep checking back in. No doesn't mean never. Stay abreast of technology, prices, and incentives. Make those no's turn into yeses. So I'm going to leave you with some contact information. Paula is really good around commercial operations and has a lot of people at the Energy Trust, PGE. She knows a whole network of how to get you some help. And then John Maloney on the major industrial customers. There are account managers. There's all kinds of support at the Energy Trust and others around industrial process. So you don't have to go through all this alone. Give a call and get some help. And with that, I'm going to turn it back to Beth.
Thank you, John. I want to remind you of some upcoming webinars that we have this summer and into the fall. You'll see a list here in front of you. Next week we have CFO's Perspective of Energy Efficiency and Renewables that John mentioned. You'll have an opportunity to find out how to talk to your CFO about doing some of those projects you'd like to do. For a complete list of our seminars, webinars, and courses, you can visit EnergyEducationCenter.com. Before we proceed to the question and answer portion of the webinar, I'd like to remind you that you can still continue to submit questions to me through chat. And within a few days, I'll be sending you a follow-up email with a recording of this session and the PDF of the slides. And at this moment, I'd like to draw everyone's attention to a polling survey, which I opened in the bottom right-hand corner of your screen. If you could take a few moments to fill that out, we would really appreciate it. We do use your feedback to improve future webinars, so we appreciate you taking the time to do that. And now I'd like to proceed to the question and answer portion of the webinar. John, it looks like the first question we've received is where do I find the amount of watts used for a specific piece of equipment?
As I mentioned, many of the pieces of equipment, especially if they're older, you may have a difficulty in reading the label, but the label is the first place you go. Other times the vendor might be called in if you have an HVAC vendor or a supplier. They may say, oh, I recognize that. That's an old Biltmore or a particular piece, and they can look it up in records. But also the Energy Trust of Oregon and the local utility will have people that have sources that can help you find something that doesn't have a clear label. So I'm back to that previous page of reach out, ask for some help. There'll be some people that are glad to help you find out. In some cases, you may even have to go to the length of doing energy data logging and some actual measurements.
Great. Thanks, John. And I think a related question we have here is about where the questioner can find energy efficiency ratings or seasonal energy efficiency ratings that you spoke about. Is there a website with that information?
For a specific piece of equipment, I don't know of a website that would give you everything you need to know. The most important thing I would say is to go to the Energy Trust of Oregon or a Department of Energy here in Oregon. Energy Star has some good information in the local utility. They will tell you here is the minimum efficiency rating needed to get an incentive. And that kind of gives you a benchmark of what is high and what is low. Until you get to those benchmarks published at the Energy Trust or other sites, you know your energy efficiency rating isn't high enough. And then the customer or the vendor will tell you, okay, here's the different levels above that. So I would say, again, call, get some advice, but vendors should be providing you with that information when they sell you. If they're not telling you the efficiency rating and they're telling you, here's a great deal, you may not be asking the right kind of question.
Great, thanks, John. And this looks like our final question for this afternoon. Let me just make sure I have this in here right. Who can help me make these sorts of calculations and the paperwork I need to do to get incentives? And I assume they mean from the Energy Trust of Oregon.
If it's the Energy Trust of Oregon, most, if not all, of their trusted trade allies, they work very closely with, and they provide templates. They provide specific forms that guide you through the calculations. So definitely, again, go to the Energy Trust website or call Paula or John Maloney, who would also be able to tell you and give you advice on how to do those calculations quickly and simply. For some of our larger groups, we pulled all the groups together. We used to have done in the past Energy Champions Workshop and pulled in a school district or two and had teachers and facilities managers and everybody involved in the room and kind of practiced some of these formulas together. So there's several ways. Again, I would say make the call, ask for some help, and you'd be surprised at how many people are out there in the industry that are more than willing to sit down and help a customer with the math and the incentives to get to a successful project.
Thank you, John. That was our last question, and I'll leave you with those contact numbers here on the screen. I want to thank John, and I want to thank all of you for joining us today. We'll stay online for just a little bit in case you'd like to chat with us some more, and we hope to see you at a future webinar or seminar. Thank you.